So apologies for the voice today, I'm a little under the weather, but we'll go ahead and push through. Today we're going to be looking at generating Metasploit payloads for an example stack-based buffer overflow program that we wrote. And we're doing this to show that while Metasploit is a fantastic tool, some inner working knowledge of what you're actually using is required depending on how you're exploiting or what you're exploiting. So we're going to go through that today and show why that's necessary. But if y'all have any questions on this file or any other files that we've analyzed, head over to ringzerolabs.com. We have a ton of articles over there, and specifically there's a link to this article below this video in the description of where you can follow along with written examples and pictures and things. But here we just show what the vulnerable application is. In our case, it's just a simple C++ program. We're generating a 1024 byte character array, and we're using a vulnerable function gets to fill that array with data. Gets is vulnerable because it doesn't have bounds checking. Therefore, you can feed it as much data as you would like, and it will take all of it. And here we just start up the program to show the assembly, which is highlighted in blue. Very simple assembly. Starts out by creating 1024 bytes or 400 hex on the stack. That's where the buffer is going to be. It then pushes that address right before the method gets, and that's where gets is going to store all of its data. So here we just switch over to the application, throw in a whole bunch of A's, press enter, and as we see, it took all the A's, and down here on the bottom right we can see all the hex 61s, which is lowercase a. So we didn't put in near enough A's to overflow the buffer. As you can guess, we need over 1024. But if we notice here, the return address that we need to overflow from our initial stack location up here, right here, the 18FB40, that's the top of our stack. We're going to fill it full of data all the way down to our return address, which is 18FF44. We need to overwrite that address to something that we control, in this case, our buffer. So we're going to show how to do that. So over on our Kali machine, we're using a program called MSF Venom, and what that is a combination of MSF payload and MSF encode. It allows you to generate a shellcode payload as well as encode it all at the same time. And here we just generate a reverse TCP interpreter from Windows. We put in our host and port and any kind of bad characters that we don't want in the shellcode. And 000A, all of these are typical characters that are can cause a string to terminate early or have bad assembly, that kind of thing. So we tell MSF Venom to encode our payload and make sure none of those characters are in it. And then over on our other tab here, we're just using MSF console with the multi-handler. We set all of our options to correspond with our payload, the host and the port, and then when we're ready to use that, we can just type exploit and it will run that handler for us. But over here back on our Windows machine, we've transferred the payload that was generated by MSF Venom. It's important to note that the payload portion is only the highlighted portion here. The EBFE at the top was added by the analyst and not MSF Venom. That's important to note. The EBFE is just 2 bytes of shellcode that tells the program to jump to the current instruction. So it's an infinite loop that will allow us to attach a debugger here in a moment so that we can catch our shellcode and kind of step through it as it goes. And then down at the bottom is just our calculations of how much junk data we need in addition to our MSF payload at the top here to overwrite into that return address. That's all that's doing, is taking essentially EBP minus ESP minus the length of the shellcode that we have, and then that number, you put that many A's in there, and that'll be all of our junk data to fill up the buffer. So to feed this data into the program, what we're going to do is use command prompt, just Python, our script, and then the name of the application. And as you see, the command prompt is kind of hung, and that's because console application 4 is hung in that loop, as we see here. EIP is at this FB40, which is the top of our stack, our buffer, and it's executing EBFE, which is jump to itself. So just an infinite loop. So we can tell the debugger to go ahead and step one instruction past this, and then we can start executing our shellcode and make sure it works. And over here on the right, you just see the stack and how it's filled up with a bunch of 41s, hex 41s, which is capital A. So here we start to execute our shellcode, and we see that the bytes below this loop are starting to change, and that's just the encoding portion of MSF Venom. I believe it defaults to Shikaraganai, and it goes through and obfuscates your shellcode. But we're going to scroll down to the first jump EAX that we see, and that is where the first Windows API is called. It goes through, the shellcode goes through and resolves APIs that it needs, stores them off, and then calls them when it needs it. So everything looks good here. The shellcode was executing correctly. Doesn't seem to be any issues. So we should be able to we'll go ahead and stop the program, and then if we remove our little infinite loop at the top, and then do our command line again, we should get a reverse shell back to Kali. But as we see here, something bad happened. We're not real sure what. Maybe it's because we didn't start the handler on the Kali box. So we go back to our Windows box, repeat the command line, and as we see here, there's still no shell. So something happened. Not real sure what. We know that our calculations were correct because we gained control of EIP. So we overwrote the return address. It went to the top of our buffer, started executing the shellcode. It seemed like it should be okay. So then maybe something's wrong with Metasploit's payload. But it's such a popular tool and so many people go through it and vet it that seems unlikely. So something else is going on. So if we add the EBFE back to our shellcode, execute the command line again, open the debugger and attach, we're going to see what's going on. So we hit go a few times, pause at the infinite loop, cool. Set the new origin past that, alright, start executing. We see the loop again, execute past the loop. Everything is now deobfuscated, great. And we go down to this first jump EAX, that's where the first API call happens. In this case it's load library A. Now the shellcode isn't calling EAX, and by it not doing that, since it's simply jumping to EAX, that means it has to push its own return address to the stack. And as we see here, it's 18FBF8. And I've put that down in the dump, down the bottom here, so you can see the bytes. So we step into load library, start stepping through it. Keep going, yep, great. Everything's good. Oh no, something happened. Just about every one of those bytes changed. And as soon as we return, now we're returning back to that FB-F8, which is correct, but all the bytes have changed. Why is that? It's important to know where your data is located. So in our case, our example here is a stack-based buffer overflow, which means all of our shellcode resides on the stack. As soon as we started executing this shellcode, the Metasploit payload did not change ESP or EBP, which means any subsequent library calls are going to push and pop values to the stack as they should. So we need to change EBP and ESP manually. And here I've just added some pre-computed shellcode at the top here, and we'll see what that is here in a second as soon as I open it in the debugger. So I hit go a few times. Now we're at the infinite loop, and now our little piece of shellcode starts here at this XOR EAX and goes to the move EBP ESP, and all that is doing is subtracting 404 hex from ESP, the current ESP, to move ESP and EBP down below our shellcode on the stack. That way any subsequent API calls or anything won't unintentionally overwrite our data on the stack. So all the pushing and popping and everything is going to be done below where our data is actually executing. Now if this had been a heap based buffer overflow, this setting up of the stack wouldn't have mattered. Doesn't matter because the heap's its own little storage space. But because our shellcode is on the stack, and because API calls are about to use the stack, things get overwritten. So if we go to our shellcode, we remove the EBFE, keep our little stack cleanup at the top, go over to Kali, make sure our handler is running. It is. And if we execute our Python script with our vulnerable application, we see that we have an interpreter session. So we can drop into show who you are, exit, just do a little get system for fun, drop into a show, who am I, system. Great, everything works. So that's just a fairly quick example of when a tool is fantastic, it does its job, but when you need to understand what the tool is doing in the background, how it works, why it's doing what it's doing, and how it applies to your situation. Again, if this had been a heap-based buffer overflow, we would have been dealing with something different, and the shellcode by itself probably would have worked without any kind of modifications. But if people go in and think that the tool is going to do everything for them, you'll run into errors oftentimes and not know what's going on. So the fundamental understanding of where your data is, what your tool is doing, and how it's doing it can lead to a much better understanding and much higher success rate when you're trying to exploit things. So I hope this was informative. If you all have any questions, comments, concerns, hit us up at ringzerolabs.com, and we'd be happy to answer anything that you have for us.